Hi everyone, my name is Josh, and the name of my research paper is called Parameter, and I'm looking at enhanced generative design tools for large-scale housing developments within a prefabrication context. So just to start off with an overview of what I'm going to present today, so I'll be starting with the why, the research problem itself, how the research has addressed the problem, what has been done about that since, and any limits, any pros, cons, and limitations of the research as a whole. So right now, internationally and locally, there's a huge shortfall in housing supply, no doubt. If you do want to build a lot of houses in New Zealand, though, you'll typically run into three main issues. The first of which is that we predominantly build using traditional construction, which at scale is expensive, it's inefficient, and you have more variables to deal with, like weather. The second problem is that because we are using traditional construction, we tend to resort to a limited typology variation. Usually we'll have 4 to 6 typologies that we'll just copy and paste, and this is usually fine when you're doing a townhouse development, but when you're doing whole suburbs and whole areas, new regions, it gets pretty monotonous and it's architecturally not very exciting. Thirdly, the problem is that we have a lot of houses at scale that are performing poorly or averagely in terms of climate performance, and the Green Building Council released a stat earlier this year, and they found that around 40% of New Zealand's housing stock is cold or damp, and that includes new houses as well, which is obviously not ideal. So my research question is, how can an enhanced generative design tool optimize building performance and make prefabricated housing at scale feasible whilst encouraging design variance in the conceptual and developed design phases? So I'm just going to break this down a little bit, there's a lot to dig into. When we talk about an enhanced generative design tool, we're talking about a generative design tool that enhances and it does not replace the designer itself. This is very important to consider for this research, and I'll elaborate on that later on. When we talk about prefabrication at scale, we are talking about en masse residential construction using prefabrication, and when we talk about going beyond encouraging design variance, we're talking about going beyond standardized typologies, really going beyond the copy and paste 4. We want to, have the ability to go to 6, 8, 10 unique designs that share no commonality in terms of design itself. So I just want to make a slight segue to another industry that had these same 3 problems almost 200 years ago, and that's actually the car industry. 200 years ago they had issues with producing high quality, low cost cars at scale with a variety of different shapes and sizes. And right now these days you can get a high quality car that comes in any kind of size or model you want, and it's lower in cost than it would be if it were made by hand. And the reason why this works is because car models are different, but they share their components. So the steering wheel from a Hilux might be used in a hatchback, or the engine from a sedan might be used in a pickup truck. So you still don't compromise your ability to mass manufacture, and you still get the benefits of economy of scale, but you can have different models and variety within the system. So why are we taking the same approach with building? And so following sort of this realization, I did a bunch of literature review and research, and sort of arrived at 6 main points. Essentially, we want the computers to do the complex stuff. We want them to deal with data and complex problems and stuff that involves lots of numbers. We want the humans to do the human things like design, circulation space, social space, things that are more ambiguous, that are more difficult to teach computers without an immense amount of compute power. And we need to use prefabrication at scale. There is no other way of achieving the same economic and speed benefits when working at scale, and we need design variance. You can't have a cookie cutter solution that works across across the site and across parts of the country in different climate zones. You need to have that variety if you want good climate performance at scale. So with all of these things considered, I then went on to do my research, and the research method I chose in the end was a mixture of research-based design and design-based research. So I started off with a literature review and a lot of research-based design, and then the predominant amount of the research was design-based research, and sort of mixing in any additional literature reviews or any additional research I needed. And this was really critical to rapidly iterating and improving the tool, and it really allowed me to tailor and focus the tool as the research progressed. So how did Parameter address this in 3 months? So it's really important to consider that computers are not good at everything, and there is no better example of this than the floor plan generation tool in Parameter. Essentially, in Parameter, it's a very simple floor plan generation tool. There are 3 main variables. All the rooms must be close together. They must be, touching each other and smack bang next to each other. There's a site conditions. You've got site boundary and an abstracted point cloud, which represents a combination of sunlight paths and data, but also points of interest, views, etc. And so the computer's able to juggle all these data points, all these considerations, and generate a floor plan. But as you can see, it's quite janky. It doesn't quite work out that well. And the reason why you need a human here is because you and I can look at this floor plan and go, if I move the bathroom up a bit, there's a corridor that runs through, and if I move things a little, it'll work out a bit better. Whereas it would take it takes the computer about 2 hours to get to the same stage. So, it's just much more efficient, and the human will make better design decisions than the computer. And this is something that I found in my literature review and research as well. In terms of what's been done after 6 months into the research period, I did a lot of rewriting, optimization, really improving the performance and reliability of results, and also just focusing and appreciating parts of the tool sort of more in line with the core research topic as well. But by far the coolest thing that has been done in this research so far is the ability to generatively optimize designs for prefabrication. So here we have 2 houses that are completely different. They share no design commonality, but they are optimized generatively for prefabrication. So we are able to take these 2 completely different houses and split them up into their constituent parts, and we end up with 2 houses, 52 components total, but only 11 unique components. And what this means is when you go to mass manufacture these houses, you can just go to the fabrication facility and say, hey, I only need these 11 variations, instead of coming to them and saying, hey, I need 100 unique parts. You can imagine it's going to be a lot of trouble to deal with. And so this actually applies when you work up in scale. Again, we have 4 different programs, 4 different requirements, 4 different site boundaries, site conditions as well, war output, and then again it only takes me about 5 or 10 minutes to adapt these floor plans and make them workable. And as a result, we have these floor plans, these designs, that have 127 wall elements, but only 16 unique parts, and that only took 1.5 hours to generate all 4 designs in total. And when you compare this to a normal house, which has 42 elements, but 33 unique parts, that's just for one house. So you can imagine, as it scales up, the really increased efficiency you would get when working at scale on these projects. To conclude, the future in a collaborative, human-generative approach brings many benefits to an industry currently struggling with an outdated approach to construction and design. Lack of innovation has literally cost us time and money, and initial research shows the potential for vastly improved quality, time, cost, and climate performance of residential projects at scale. The full thesis research will address a lot of the limitations found in this research period and work towards producing 4 distinct typologies or more to prove how practical the system is. So thanks very much for watching my presentation. I will be sticking around, of course, for any questions, so feel free to ask anything, and yeah, enjoy the rest of the ASA conference this year. Cheers.